Okay, we'll quickly go through what happened in the last class. So what we said was that any 2 pi periodic function can be expressed in terms of the basis functions, and the basis functions are cos nx, sin nx, and 1 by root 2. And if we are going to claim that these are the basis functions, I say claim because we have not shown that these are the only functions that are required, but the mathematicians have shown that any 2 pi periodic function can be represented in this particular form. Okay. And the coefficients are, like we have said, from the parallel of the vector space that we talked about. The coefficients are going to be the projections of the function on the particular basis functions. And so an is the inner product of f and cos nx, bn is the inner product of f and sin nx, and a0 is the inner product of f and 1 by root 2. And when you do all this, you are going to get the so-called Fourier series. And the periodicity does not need to be minus pi to plus pi. It can go from minus L to plus L. And you can just map the x to some dummy x star and say that you are going to go from 1 by L minus L to L fx cos n pi x by L dx. So the ANs and BNs can, and then you can put pi equal to L. So AN is integral of 1 by L minus L to L fx sine n pi x by L. And if I put L equal to pi, then this guy goes away and you get a minus pi to plus pi, and this is 1 by pi. Okay. So AN and BN, sorry, this is BN, doesn't matter. So AN and BN are the coefficients of the basis functions, and some things that we need to be careful about. The series is assumed to be a convergent one, which means that fx is integrable. That is, you need to be able to find out what the a0 is, and fx times sin x and fx times cosine x also need to be integrable, and the series has to be a convergent series. Once we are clear that these conditions are satisfied, then we can go ahead and say that we have the solution to the series for any 2 pi periodic function. Okay. Then what we said was that there is this nice theorem which says that if fx is a piecewise continuous function, and the piecewise continuity is defined as if you are going to have something of that nature and there is a discontinuity, could be more discontinuities. So your gradient should be existing when you are going to come from either the left or from the right, and everywhere else the continuity of the function is going to be present. So if you have got a piecewise continuous function, then we can say that the Fourier series is going to exist for such a function, and that guy is going to converge to the midpoint of this. Okay, so that's something that we need to look at, and I'll show you a small routine which is going to indeed show that that's the case. That's a theorem. We are not proving that theorem at all. That the mathematicians have done, and we are just going to be using that relationship. Okay. Then we said that we can have functions which are either even or odd, and an even function is somebody who is going to have f of x being equal to f of minus x. That's an even function. And if you are talking about an odd function, then the odd function is going to be somebody who looks like so. And so this guy is going to be f of x is minus of f of minus x, and that guy is f of x equal to f of minus x. And if you've got an even function or an odd function, there is a small advantage in algebra that you get. All functions need not necessarily be either even or odd. There could be functions which are neither even or odd. There you have no option but to do the entire algebra. Okay. So if f is even, then you can say that integral of minus L to L fx dx is going to be 2 times integral 0 to L fx dx. These are small advantages in algebra, but sometimes they do become somewhat significant. So in the case of the Fourier series, when we now go ahead and look at the coefficients, if you are having an fx which is going to be an odd function, so if this guy is going to be an odd function, we know this guy is an odd function. So odd times an odd function is going to give me an even function. And if I'm going to have an odd and an odd giving me an even function, then I can just go ahead and say that this guy, instead of 1 by pi, I can just make this 0 to pi is equal to whatever bn. Okay, and if this guy happens to be an even function, then even times odd is going to be an odd function, and therefore I don't need to do any of these algebra. I can just simply say that this guy is going to be equal to 0. So in some sense, half of my algebra is going to get saved in some sense. Okay, but it's not necessary that you need to use any of this. You can assume that fx is going to be either even or odd or neither even nor odd, and proceed with the calculations. And here is something that shows you that perhaps what is a fortification of the even and odd function business. Sine theta is an odd function, cosine theta is an even function, and when you are going to plot cosine theta plus times sine theta, it's an odd function times an even function, you end up with an odd function, top right hand corner there. And when you have a cos function times a cos function, it's an even times even, you end up with an even function, and similarly your odd times an odd. So this is where we quit last time, and we started looking at an example, and if you are talking about a periodic square wave, so this guy is a periodic square wave. I've got a square wave here, so this guy is a periodic wave, and then this guy keeps on going. What we notice is that there is a discontinuity here, but we don't care. We say that the Fourier series is going to be able to handle it. So we did the algebra, and we said that this guy is an odd function, but nevertheless we are going to compute all of the variables. So this guy is an odd function, and therefore if I'm talking about an an, this is going to be f of x cos of n pi x by L minus L to L 1 by L. And because this guy is an odd function, this guy is an even function, so I don't need to do any algebra, and I just am going to put these guys equal to 0. Okay. Similarly, you can now get the Bn for this guy here. Bn is minus L to L 1 by L. L happens to be 1 here, so this guy is 1, this guy is 1, and I'm going to say now that I have got an f of x sine of n pi x by L. L is equal to 1, and now when I have got minus 1 to plus 1, there is a discontinuity in between. So we said I'm going to go from minus 1 to 1, whatever is there inside. We'll do this once more today. And then I'm going to minus 1 to 0, sorry, and 0 to 1, and whatever is there inside. Okay. And then you can just go ahead and do the algebra, and you are going to end up with that. So this is where we were when we quit last time. And now we'll take a couple of more examples before we go ahead and say that we understand this business of the computation of the Fourier series. This is a slightly more involved example. So there is a this is a sawtooth wave, whatever that may mean, but the function that I have now is something, again, all these are discontinuous functions. If you have got a continuous function, there is no problem. Even with a discontinuous function, this is a piecewise continuous function, right? Because there is a discontinuity here. So at this point, there is a discontinuity, at this point there is a discontinuity. So the Fourier series is not going to give me the value, or the Fourier series is going to give me something in between. What that something in between we have seen. So if this guy is like this, the Fourier series is going to give me a 0 at this particular point, because it's a continuous function. Okay. So this discontinuity it's going to recognize in some sense, but it's going to say that this guy is going to become equal to 0. Okay. So let's just go ahead and once again take this thing here. This is again an odd function, and therefore you are going to have, these guys are going to become equal to 0. The only thing that's going to survive is sine of x. So this guy now is 1 by L. L is equal to, okay, I've just kept that as, okay, L is 1, so you can just take this L1 here or at the end. So fx here is x. So an is 1 by L minus L to L x sine x times this. And now let us say that we realize that this guy is an even function, right? Because this is an odd function, this is an odd function. So the product is an even function. So instead of doing what we had done for the previous example, we just say that this is going to be 2 by L, 0 to L, x sine x by L. So this L is equal to 1 in this particular case. Okay. So this is my function, and integral of x sine x, we need integration by parts. Okay. So our mid-sim Midsem is on 24th of February 2:30 to 4:30, and the room I still don't know. I'll put it on Moodle. But for the midsem now, we have not done many things like integration by parts, maybe use of the Leibniz rule, or maybe partial fractions so that you can compute the Laplace transforms of certain functions if you want to do it. So all of these have not been done. So this and maybe differentiation of a product, which some of you had trouble. So these things have not been formally done, but from your earlier calculus course, these are expected from you. Okay. All right. So we do an integration of parts here. So this guy is 2 times integration 0 to L. So this is the first function into integral of the second. Sine integrates to a cos n pi x by L upon n pi by L, and sine integrates to a minus cos. So there is a minus sign there, and this guy is going to be 0 to L minus integral of the second, which is cos n pi x by L upon n pi by L times the differential of the first. This is zinc, and this is going from 0 to L. Okay. So such manipulations are fairly straightforward, and you are expected to be able to do such things. Okay. So the algebra you can go ahead and now look at. So we have got the first guy there, and then there is an integral here. Go ahead and do the algebra, and you are going to get what is going to be your Bn for this particular case. An happens to be equal to 0. An is 0, A0 is equal to 0. Typically n is going from 1 to a very large number. All right. So we'll take one more example, which is now an even function. And this now has got a discontinuity in the sense that the slope is not continuous. So this is the function that we are talking about. So I've got this as equal to x square, fx is equal to x square, and the function is continuous, whereas the slope is discontinuous, but Fourier series doesn't care. Okay, it's going to be able to handle it. Okay, so I've got fx equal to x square. Now this guy is an even function, and therefore the Bn terms are not going to be there. Okay, so the Bn's are going to become equal to 0. Now we don't want to write that again. It's only the An's that I need to worry about, which means the A naught also is going to be existing. So A naught is going to be integral of fx dx, and you can either write it as fx dx, or like he was pointing out, you have the 1 by root 2. I've corrected the slide there. You were not there, but the corrected version is there just now. Okay. So you can use a naught equal to fx dx, or you can say that a naught is fx dx 1 by root 2. If you put this 1 by root 2 there, you will have a root 2, and if you don't put this here, there you will have a 2. Okay. So a naught, this is what is standard done in most of the textbooks. So we'll just go ahead and do this. Minus L to L, 1 by L. So fx is x square. In this particular case, you can go ahead and integrate it, and you are going to get a naught equal to that. Similarly, you are going to get an is equal to x square cos n pi x by L, and now we have done the algebra a few times. I don't want to do it. All the algebra is given up here. You can go ahead and come up with the final value. Okay. So the algebra you are expected to be able to do. This is one last example where which is also an even function. The only thing I want to point out in this particular example is that in this particular case, there was the other example that we saw where we had this, right? So in this particular region from 0 to L, this is minus L. So 0 to L, the two functions are identical. From 0 to L, the two functions are identical. Whereas when you take minus L to L, this became an even function, this became an odd function. Okay, so we'll talk about this a little bit more later on. But that's the reason why I have picked this example. So we have already done this. The algebra is all done, except that in the earlier case we had a sine. In this particular case you have a cosine, because this is an even function. Earlier case was an odd function. You can use either of these formulations. If we are only interested in this region here, right? If we are only interested in this region and trying to say that I would like to represent that, or whatever may be the reason, fx equal to x is much easier than an infinite sum of sines and cosines, but we'll see why sometimes that becomes necessary. If this is the only region, then both this formulation and this formulation are going to give you identical results. Okay, that's the beauty of this. Okay. But anyway, when we are saying that this guy now is this type of a wave, whatever you may want to call this wave, can do the algebra and it appears that the representation is slightly different. Okay. So if suppose you were told to represent that curve in a series, then you can brute force say that I'm going to do the algebra for that, or you can say that I have the algebra in the slides and I'm just going to take 0 to L and use that summation. You are perfectly fine. You can also say that I'm going to brute force make this as the function and I'm going to represent the function. Either way is fine. So what you are trying to say is, if I have only this guy that I need to model in some sense, if you will, you can either make this like this function, you can make this like this function, or you can keep it like this. Okay, all three options are there. As of now, we have seen this option and we have seen this option. We'll formally look at it in just 1 minute. Okay, so you get all these guys, and before we go ahead, let me now show you what so this was all kind of some kind of abstract sense, in the sense that I'm telling you that these are ANs, you sum them up and I'm telling you that they work, but do they really work is something that I'll just show you. And I have this now. The online tools have started to dry up. I don't know if any online tool is there that can represent Fourier series. So now one has to do the coding on your own, fairly straightforward. I find Excel is, so here is what is the first example that we had. Okay, so I just brute force just took whatever we had, which is this one here, and I just put in the summation, nothing else I have done. Okay, exactly this whatever we have on this slide, I have taken and I have made it into a summation. Okay. And if now I say that I'm going to take, now I start taking uh, uh, terms, number of terms. Let me just play with the number of terms. So here I have taken the first 5 terms now, and if I go ahead and execute it, okay, so if I'm going to take a very few number of terms, okay, so remember we have to go up to an infinitely large number of terms. How infinite is infinite, we don't know. Okay, but if you take a few terms, what you see is that already it is looking like the wave that I want it to look like. Okay, if I make it fewer, then it will become worse. So if I just take, let us say, 2 terms, in this particular case it will become worse. So if I take only 2 terms and then suppose I execute this guy, oops, something new, okay. I only hope I did not change something that I should not have changed. Okay, so I just took 2 terms. Okay, when I took 2 terms, that guy looks like a sine wave. Okay, and now as and when I have increased to 4 terms, that has become, or 5 terms, that has become that. And now let me just make it 50 terms. Okay, so now you see that the 50 terms is the one that is almost looking like the square wave that I wanted. Okay, so let me get rid of the other guys so that we can just see only the 50 terms. Okay, so it looks pretty good now, right? So it's the square wave that I wanted. But what you notice here is that there was a discontinuity. There was a discontinuity, and the Fourier series is going to converge to the center point there. Okay, so that's something that we need to be careful about. So this is a discontinuous function. Now what is happening here is something that we are not going to talk about in this particular course. At the moment we just appreciate the fact that even if you make it 500 terms, that will not go away. So it will just keep on staying there, and there are reasons for that, and the electrical counterparts are going to be more worried about this. We are not going to be so worried about that. So if you see, I have just put a huge number of terms. Okay, so it's pretty much looking like what I want. Okay, but still at this point here, it is having trouble. It's not exactly that square wave that I wanted, and that little blip is always going to be there. Okay, okay. So now let me go ahead and show you the other square wave, which will not have these problems because the function was a continuous function. There was no discontinuity as far as the function itself was concerned. So let me just show you the quadratic that we had, and just give me 1 minute. Okay, let me hope that it works. Okay, so I just had now 5 terms. Let me just make it 2 terms like we had done before. This pretty good actually. See, because there were no discontinuities, you can see that the 2-term solution, 5-term solution, they're all pretty similar to what we were trying to get, which was this one here. And once again, I have just brute force taken the solution from here, which is this part here, and I have just put additional number of terms. That's all I have done. Okay. And if you see this guy here, 2 terms, 5 terms, all of these are just not, so it does a pretty good job, very fast actually. Just 2 terms was that. Of course, I can make it 500 terms and it becomes really good. So, okay, so this is almost perfect. Whatever I had. So there was no discontinuity, so this guy is doing exactly what I want. Okay, so at that particular point of discontinuity, there were a few oscillations. There are reasons for that, and we don't want to discuss that in this particular course. But what I am trying to point out is that if you are going to have, now we can get rid of this. So we had seen that in the previous class, we had seen that there was a theorem that is going to tell me if a function is piecewise continuous, right? So this guy here is piecewise continuous, and so is this guy here. Okay, so the functions are continuous in some sense, but the Fourier series is going to converge to the center point of these two, as we have just seen when we were looking at all the terms there, or it is going to, so there is nothing like a center point here, it converges to exactly that number there. So if you are having a function that has a discontinuity, indeed that theorem is a very useful theorem for you to have under your belt. Okay, so that's what this whole exercise was all about. And now let us continue. So what we are saying is that that theorem is a very useful theorem, and when you had those discontinuities, it's going to tell you where that particular Fourier series is going to converge to. Okay. So if this was a wave like this, maybe, I don't know, and this is something like that wave that we talked about, it will converge to some point there. So if there is a discontinuity and it is piecewise continuous means that this guy is continuous, the derivative, this guy exists, the derivative, when you are coming from here, when you are coming from here, and the midpoint is where the Fourier series is going to converge to. Okay, so now let us go ahead and say that this is something that we said a little while ago, and now let us formally look at this. Suppose I have got a situation where this is some kind of a function which is there, and I would like to go ahead and in some sense model this. Okay, I would like to let us say get a series which is going to be representing this. We said that you could go ahead and take this part, make it an even function. You could go ahead and make it so like so, make it an odd function, or you could just leave it like this. Okay. Now the question is, what is it that the series is giving you? Okay, what is the series giving you? Okay, suppose you have done this. Okay, suppose you have done this. This is 0, this is L, this is minus L. If you did this, then this coupon is going to repeat itself. And if therefore, okay, now the series which is there, which you have, it means that we have said that if you have an x here, it's going to give this point here. If you take an x which is here, it's going to give you that point there. If you take an x here, it's going to give you that point there. Okay. The series has got an x inside it. So in this particular case, which looks pretty much like this, your x can go from anywhere to anywhere. Okay, so that x which is floating in there, it can be anywhere actually. Okay, so if the x is here, you are going to get this point here. If the x, so anywhere you have the series is going to give you the value of the function which is like this. Now suppose you model this like this. You were only given this curve here and you were told you get me what is going to be the variation of the curve here or representation of this curve fx as some kind of a summation. And you went ahead and brute force extended it like that because one of those terms an's or bn's are going to cancel off. And now the function now is going to be looking like so. This is what the function is going to be. So all of these guys which are there are going to give you the solution at any x you want. And if you are going to now say that I don't want to do any of this stuff, I'll just brute force only take this and represent this as a Fourier series, then this is what is going to come out. So all of these are possibilities that can happen. So let me just once again clear up any, so that blue guy which is given there, that's the given function that I'm trying to represent as a series. Okay. There are different ways in which you can represent that blue guy as a series. Okay. One way is to say this, which is the red curve that you are seeing there, and then it goes ad infinitum. The other way is to make it an even, what you see is that purple graph there, and the other way is to make it an odd, which is the green graph that you get. Okay. So each of these is going to give you a coupon which is going to be different in the periodic minus L to L domain. From 0 to L, everybody is going to give you this, but if you pick an x here, so suppose now you model this guy, like this. Remember, this is the only graph that has been given to us. You are now modeling this like this. We'll see what the equation is in 1 minute. So, but now you thought this is what I would model it as. So you will get this as the coupon that repeats itself. Okay. So this guy, this guy, this guy. So if you are now saying that I'm going to say this is my 0, this is L, this is 2L, 3L, and so on and so forth. At a particular x, this particular model gives me the same value for this guy and this guy, but when you are going to go here and say that this is my x, so this model is going to give me this number, this model is going to give me this number. So if you have a periodic function, it is prudent on your part to see what is it that I want at large values of x. At a particular value of x, all of these numbers are going to give you this, all these formulations are going to give you the same result. Okay. So let's see what these formulations are all about. So let us now just go on a conceptual plane and say that I've got this is my function that I'm trying to talk about, and let me say that I'm going to represent it like so. So this is an odd function. And there's a reason why we are looking at all of this. So this is an odd function. So if an odd function is there, what happens to a0 and an? They are going to become equal to 0 because you have got odd function multiplying with the cosine term. Okay. So if this is an odd function, only the ans are going to survive. So only the ans are going to be surviving, which is going to be, this is an odd function, sorry, only the bn's will survive, which is the second one there, which you see in green written up there. So bn is going to be fx sine of n pi x by L 0 to L 2 by L. Okay, so that's the green guy there, and if I'm going to represent it like this with a naught equal to 0, then the curve that I'm going to get is going to be this, and the coupon will repeat itself. Okay, so any x you want, you will get the solution by looking at the a's and only the b's in this particular case. Okay. So this coupon is going to repeat itself. So this is the solution for the green guys. Now for the purple guys, we are saying that we are going to assume that this is the coupon that repeats itself. And now only my a naught and an will survive. This is fx cos n pi x by L 2 by L 0 to L. So this is something we have already seen so far. Suppose now that I don't like it, and all functions need not necessarily be representable as even and odd functions. So we say that I have got this guy here and I want to represent it like that. So what happens? Previously, when we had represented it as an odd function, then only the green terms had survived. When we represented it as an even function, only the purple terms survived. And now we are just saying that this is some function, and which means that both the sines and cosines are going to be existing. Both the sines and cosines will exist, which means that a naught is integral of fx dx 1 by L minus L to L, but an, okay. Now what is an going to be? That's something that we need to be careful about. This guy is 0, this guy is L, this guy is 2L. Let me call this as 2 times little l. Okay. So 2 times small l is the period now. Okay. This is a period, this is a period, this is a period. So the 2 times l is the period. So an is minus l to l, 1 by l, basic brute force definition, nothing else. F of x cos n pi x by little l. Remember, 2l is my period. So this is my period, this is my period, this is my period. So I've got 1 by l minus l to l, and I'm going to go like so. Now, this guy can be made 0 to 2l. This is what we have seen, right? That's the period, right? So I can go from minus L to L. Here it is not that great to go from minus L to L. We go from 0 to 2L. So 2L is my period. So I go from 0 to 2L, fx cos n pi x by L. Now 2L is an artificial period for me because cap L is the actual period. Okay. So capital L is the actual period. So little l is L by 2. Okay. So little l is L by 2. So this will be capital L by 2, L by 2. Okay. And 2L is equal to capital L. Now look at this guy here and the guy who is sitting up there. Okay. The two look very similar, but they are not. That's what we want to point out here. Okay. When you are trying to get the Fourier series expansion of this type of a function, I'm having an an which is 2 by L fx cos 2n pi x by cap L, where cap L is the period. Okay. Whereas here the same thing, it appears the same thing. 2 by L, 0 to L, fx cos n pi x by L. But what is the cap L there? It is the half period. Okay, it's not the full period, the 2L. So that's one thing that you need to be careful about, because sometimes when you will see these things written up, sometimes people are going to use the full period, sometimes people are going to use the half period. When you are exploiting the even and odd function representation, you are going to get the 2 by L. Okay. And if you don't have the odd and even function type of an exploitation, you still have a 2 by L. Okay. Both of them appear to be the same expression, but both of them are not the same. Okay. Because there is this 2 hanging in here. Okay. So, but otherwise it looks the same, but they are not the same. You have to be very careful with that. That's all we want to point out here. Okay. So the period is different for the two. The period is 2L for the even and odd functions, but the period is capital L for the combined function. The periods are different. Okay. So when you write these guys, or when you are going to represent functions in the Fourier series, you have to be a little bit careful. If you are using this type of a formulation, right? When you are using this type of a formulation, okay, so this is what you are going to be getting. When you are using this type of a formulation, this is what you are going to be getting. Okay. The reason I am harping about this so much is because we are now going to go ahead and say that we are going to try to work out the solution to an ordinary differential equation which has got a right side, which is going to be now represented as a Fourier series. Okay. So which means that you need to decide whether you want to use this formulation or you want to use this formula. The choice is yours. Okay, hopefully that is clear. If it is not, it becomes a little more clear when we do this here. So I've got an ODE. I've got an ODE and we would like to solve this ODE. So simple ODE, y double prime plus a1y plus a2y is equal to fx, and now this is a periodic function. One can take the Laplace transform of periodic function, we'll do that later on. Okay. As of now, we have got a right hand side, and what you will be given as the right hand side is going to be this. Let us say, suppose I give you this and say that now this is repeating ad infinitum. Okay. So which means that the right hand side, there's one way of solving it is to say that I'm going to have an infinite number of the Heaviside functions, a large number of Heaviside functions. Okay, that's one way of looking at it. Extremely messy, because we have already seen that even one or two Heaviside functions make the algebra fairly messy. So if you've got a periodic function, then the best way, or not necessarily the best way, as of now, the best way for us is to represent this guy as a Fourier series. Okay. So this is given to you, right? And if you have to represent the right hand side as the Fourier series, this is the formulation that you are going to be using. If, however, we say that the right hand side was this, then you have another Fourier series. So if the Fourier series on the right hand side is given to you, then it's your responsibility to put the correct variation of the Fourier series. Okay. But if you are told that only the right hand side is just this function and not a periodic function, then you can use any one of these series. All of them are going to work. Okay. So if only this is given and this is given, then you can say I'm going to use any formulation I like. Brute force, I'm going to make this because I like this, because this does not have this problem of getting me a different number at this particular point. But you can use this, you can use this, or you can use this. All of them are fine. Okay. Whereas if I give you this specifically, or if I tell you that this is what the system is going to be like, then you need to put the correct formulation. Okay. All right. So in this particular case, let us assume that you have used the correct formulation. So the correct formulation has already been used, whatever may be the fx, and then you have got the fx. Let me just say that it is a naught plus a naught by 2 plus summation of an cos n pi x by n. Just let us randomly say that. Okay. So it is an even function which you have modeled, and this becomes equal to this. Fairly straightforward. I can get my complementary function c e to the power r1 x plus c e to the r2 x. This is my complementary function. How do I get my particular integral? What is my particular integral? Okay, we'll stop here today.